we're going to dive into some applications of all this calculus stuff that you're starting to learn. One of the first applications of using calculus is for projectile motion. Usually something going up in the air and coming back down, and just being able to describe when it actually gets to the very top, how fast it's going when it hits the ground, simple questions like that. And we're usually given an equation, right? And we just have to use this, find its derivative to find speed or instantaneous speed, and just answer all the questions that are given to you. Okay? So a few things to think about. When you throw a ball or something, kick a ball up in the air, it initially goes up really fast, but then it starts slowing down as you get higher and higher and higher. It slows down, right? And then at some point it hits zero. Right? It's still for an instant moment, just for an instant moment, it doesn't have any speed. It's just in the air, and then it starts coming back down, right? And so since you're coming back down, these are all going to be negative speeds, right? So we have to know that at the very top, there's a zero speed. So that means in calculuses that the derivative at that point, if it has no speed, is zero. So if you want to find like how long something takes to get to the very top, the question to be asked is, well, where is the velocity zero? Because it's going up and up and up, slows down, hits zero, then goes negative, negative, negative. Okay. So we just have to learn what all these questions mean, just using the math symbols. We also have to know that this is symmetric. So for objects that are relatively small, thrown by a person or something like that, they do follow its parabolic curve. And at the very top, that's like the halfway point. So if you know, like let's say it takes 10 seconds to get here, right? We can assume that, okay, it's going to take 20 seconds before it hits the ground completely. So it's 10 seconds to go up, 10 seconds to go down. That changes if you're doing heavier objects and you're taking into account different elevations, different atmospheres, different wind patterns. Then those numbers can change. But if we're just out in the field, just throwing an object up and down, it's pretty reliable. Okay, so that much we have to know, and I think that's about it. Yeah. So all we gotta do is follow the curves and make sure we know what we're going to use to answer the question. So if it says how far or how long, we can use our distance or our height formula. If it says how fast, what's the speed, that's when you want to use the derivative. Okay, and you have different options of doing things in different ways. I highly recommend you kind of follow how I show you. It'll save you time later on. Okay. So we want to find the instantaneous speed. So if you see the question says speed, you know it's going to be talking about the derivative. All right. Anything with speed, we've got to find derivative. All right. This will tell us the height of an object, and it says right here, it'll tell us the height of an object. If you give a time, like after 2 seconds, you plug in 2, it tells you how high it is off the ground. But for speed, we need its derivative, right? We need to know something different. So go ahead and find f of t using our limit formula, definition and limit. All over h. And it will take a little while, but it's a good little warm-up for us to remember how we did this last week and what we did on the quiz. So take a moment and go through that. You don't need to copy it. You should already know how to do this, right? So if you need to check as you go, that's fine. But definitely do it on your own. Try it on your own. Something we want to be very comfortable with. So, should get negative 32t plus 96. And that is a new function, right? That will give you how fast it's going. So the first one gives you how high it is or off the ground. This derivative is how fast it's going. Right? So we still need to answer the original question. It says when t equals 2 seconds, how fast is it going? So all we need to do is just take right here, find f of t. I'm sorry, f of 2. F of 2. And that'll tell us the speed that's going at 2 seconds. All right, and that happens to be, let's see here. Is that 64? So that's 32. Yep. So 32. And what would be some good units here? Since we're talking about speed, what are some good units? What per second? Close. Yeah, so we go back to the original. It says the height is given to us in meters. Yeah, so now 32 meters. Think about how long that is. It's close to 50, like 50 yards, something like that. 40, 50 yards, and it's going that far every second. That's moving pretty fast. So on top of getting your answer, think about what it actually means in real world. And obviously this is just a simulation here, but ask yourself if it's realistic or not. And could someone really throw a ball that fast? They'd probably be pitching for the Dodgers if they could. That's a very, very fast throw. All right, so we got our first answer. We know at 2 seconds. All right, at 2 seconds, it's going 32 meters per second. So this is one of the reasons we use this notation with functions, is that we can actually see what our input is and what our output is all together in our final answer. So we can read it 2 seconds. At 2 seconds, we're going this fast. All right. All right. Next, find the maximum height. All right. So this goes back to what I mentioned earlier. To find the maximum height, how fast is the ball moving when it's at its maximum height? How fast is it moving? So it goes back to this. It goes up, boop, goes down, but at an instant, it's 0. It's not moving at all at the very top. So if you want to find how fast something's moving at the very top, that's when its speed is actually 0. Right? When the derivative here is equal to 0, speed's equal to 0. So we just have to take our function right here, right? That tells us how fast things are going at certain times. And find out, you want to know where this notation on the left says how fast it's actually traveling at that moment. So we want to find out when this equals 0, when it's not technically moving for that very brief instant. Notice how we're not plugging 0 into this. That tells us how fast it's moving at 0. We want to know the answer needs to be the time, because it's saying how long does it take. So we're looking for time as your answer. So you just solve this. 32t equals 96, and you get 3 seconds. So we have found that this is 3 seconds right here. I'd make this 2 seconds. Let's say 2 seconds right here, 1 second right here. And we just found earlier that at 2 seconds, it was going 32 meters per second. So that would be right around here. Right, at 2 seconds, right here, we found out it's going 32 meters per second, which is the slope of this line. If we found the slope of that line, That's the same as the speed at that time. And naturally, after we find out, well, here's where it's at its maximum height, we want to, oh no, here's where, yeah, here's how long it takes to get the maximum height. They ask, well, what is that height it actually gets to? So what formula should we use? Should we use the original function, or should we use the derivative function if we're trying to find height? So this is where understanding what you're doing is really, really important, right? So which one will give you answer that's height? Think it up. Think it up. Make a decision. Come up with a reason. Justify your answer. Yep, that's it.
The original, because when it gives you the function, it says it's measuring the height of the object.
There you go. Because yeah, this function says this is after 2 seconds, it gives you the height of the object. What this question is asking, find the height. Right? So we have to be able to put these and make these connections, right? Otherwise, it's not going to work. There's going to be too much going on. We're going to have even second derivatives and all this other stuff going on, and we cannot do this by memorization when you have so many different moving pieces, right? So that's the biggest thing moving up to calculus, is that you have to understand what it is you're doing and what your functions actually mean, right? Rather than just try to go on autopilot and let me just do the same steps as the last problem and get the same answer in the same way, and just kind of do everything by mimicking, right? Because the questions will be different from one to the other. So we got our original function, right? This is what gives us distance, so we're going to use this original function, plus 96t. Right? And now we know when it's at its highest point, and that's at 3 seconds. So we find what is the total height at 3 seconds, because that's the highest point, what we call the vertex. So we get negative 144, I believe. 9, yeah. Yep. That's Pythagorean triple. And then plus 300 minus 12, 288. Okay. So that equals 144. How about that? Pretty good, pretty good. It's almost a correct answer. What else should I add? Units, which are meters. Or meters per second. Which one is it? Just meters. Question was height. We use the function that gave us the height, right? And height is measured in meters. There we go. Good. So these two together are actually the same as the vertex, or that word from algebra. So that's 3, 144 if you're actually plotting these and on a coordinate plane. And we could also call this 3, right, we could say that that's the same as the time at its maximum height. So our t sub max is at equal to 3. All right, so what is the next one? How long is the object in the air? So when is this thing, how long does it take this thing to go up and come back down and hit the ground? We know the top here is 3 seconds. How long does it take to get back down here? 6 seconds, because 4, 5, 6. It's symmetrical. So mentioned earlier that at the top is the halfway point. So if we know it halfway up, or when it's at the very top, it's 3 seconds. That must take the same amount of time to get back down. Again, not true if we have all these other factors included, like wind and different atmospheric pressures and whatnot. But for what we're doing, yeah. So it's up in the air for 6 seconds. Okay. So we can say the time that it's in the air. So T sub air, I'm writing it, is going to be 2 times the time it takes to get to the top. So 2 times 3. 6. And then units, seconds. All right. And lastly, what is the speed when it hits the ground? Always a big question is, how hard is this thing going to hit the ground? Right? If you're doing things with like all the space rockets up there that come back down, they got people inside. They want to know how hard that thing's going to hit the water and make sure it's not going to disintegrate, right? So they have to control that speed. So how fast is this going? So what function should we use? It's asking speed. So that's a big hint. Which one gives us speed? Derivative, right? So I'm going to take our derivative, the same one over here. Which is negative 32, right? 32 plus 96. And what time should we put in? Because it takes time right here. So what number should we evaluate this at? 6, right? So we know that this over here, when is it hitting the ground? Right here at 6 seconds. So without understanding what you're doing, you won't know what numbers to put in here. So you have to know not only what function to use, but what value to use as well. And they're always changing, right? Now, 2 questions are never the same. So it's not something you can just memorize how to do it like you're doing a slope formula and just take 2 points, find the slope. Okay, let's do that again and again and again, because the problem is always changing. The questions are always changing. So we get an answer of? Thank you. Negative. Does that make sense? Ooh. Yeah, it's going back down. And if you go back up here, yeah, that would be the slope of this line right here, which of course is a negative slope, so that does make sense. So we should be able to know that ahead of time. Whenever we're finding when the object is hitting the ground, the answer is always going to be negative, assuming it went up and came back down, right? As long as the ground is below you or beneath you, that velocity will always have to be negative, right? That's always a negative value. All right. So on top of, of course, doing some of this, doing and solving these problems, use the notation you're seeing here, right? That's part of learning the math, is knowing how to notate things. It doesn't have to be exactly, but you need to use something. So like on this one, you don't want to just say, oh, it's just 2 times 3, 6. No, right? Be very clear of what it is, what you're using, how you got it, showing your thinking. All right, so I'm going to give you this right now, which on the back of it, it has a problem like this. So you can start on that, on the back. The rest of it's just going to be review. This is something you can start whenever you want, but technically tomorrow. It'll be tomorrow's and Wednesday's assignment for you to practice on. Okay, they will take a little bit of time to get used to, and I'll post on Classroom some example problems just to help you get started with them. Okay, so that's going to be for today, tomorrow, Wednesday, and then Thursday there'll probably be like a Delta Math or a IXL on there for you. So just check ahead of time. All right, let me pass those out and get you started.